degeneracy in that hadron species.
Recording is on.
Hi, recording is on. All right, so of course, if it's perfectly equilibrium, you can then assume that Fi here is some equilibrium distribution function appropriate for the hadron of species I. But in general, this system is not in perfect equilibrium on this hypersurface. So typically what you do is you take some equilibrium distribution plus some assumed to be small perturbation, which is called delta F, which encodes the viscous correction to the one particle distribution function on this surface. So that's this red point. We need a form for Fi on the freeze-out hypersurface in order to convert the fluid back into particles. Now, in practice, these particles that are produced on this hypersurface are what's called the primordial particles. They then have to feed down if they're resonances or undergo hadron rescattering. That happens later. I'm primarily concerned with how we convert the particles on this hypersurface. So first, let's look at the first part, numerically solving the viscous hydro equations. Now, this is now kind of standard. There's many groups that can do it. Here's some pretty pictures for you to look at of a central collision, I think at 2.76 TeV. This is ideal. This is including shear. This is now shear plus bulk, and going down is increasing time. And you see the normal, kind of fancy pictures you see coming out of hydro in each of these three cases. Now, of course, the question is, should I trust this simulation? And how do we have some sort of control parameter in the code that tells us if things might be going wrong? That control parameter,
Mike?
Yes.
Excuse me, the X and Y axis on these plots?
So this is the transverse plane. So what we're looking at here is rapidity equals 0 slice. This is just the overlap in the transverse plane of the two nuclei, and this for a head-on collision with fluctuating initial conditions. And then as we go down, we see that it's expanding in space. And then depending on the values of the transport coefficients, you get sort of different profile pictures, but overall it's doing the same. It's expanding and cooling down. Yeah. Clear?
Yeah.
Okay. So you can run sub-simulations, you can put curves through data, but then what you would like to do also, as I said, is try to assess whether or not you've broken any of the hydro assumptions when you were running the code itself. So what are the basic hydro assumption that we use in practice when we convert to particles in particular, but also for deriving the equations themselves? It is that we can take the energy momentum tensor and decompose it into some ideal part plus some viscous part. Now this includes the shear and the bulk contributions. And if this is to be a good approximation, of course, pi mu nu, if we assume we're near equilibrium and we want to use linearized theories to get what's going on, then this should be small. So we can quantify that by constructing what's called the inverse Reynolds number. There's two of them. There's a shear inverse Reynolds number and a bulk inverse Reynolds number. The shear is just the contraction of the shear part of this tensor with itself, scaled by the isotropic pressure, because this is the correction to the pressures. And likewise for the inverse bulk Reynolds number, in this case it's just a scalar for the bulk viscosity, and then you have to scale that by the isotropic pressure to know how big it is, because of this, that's what it's correcting. So you can go back into these pretty pictures that I showed you on the last two slides and try to extract some information about how well is this working by looking at the magnitude of this number, the inverse Reynolds number. So what's plotted here now is different. Now what I do is I just took a line along z and y is equal to 0, and then this is the initial condition is right down here on this line, and this is like a space-time diagram now as a function of time of the system expanding. And what's plotted here now is this inverse Reynolds number for the shear. Now we see a few things. One is, what is the scale here? Going up to 1, if it's ever black, that means that essentially this correction has become as big as this guy. And if it's anywhere that's, if it's like red up here, it's bad. And if it's blue down here, then this thing is getting small. So what we see is that at very early times, this shear Reynolds number is quite large. But by about, let's say, 3-4 Fermi over C, this thing is getting blue in this region, so we're okay. I've put two illustrative hypersurfaces here. One is if you were to freeze out at 200 MeV, that's this hypersurface that was extracted from this run. And the other one is this one up here at 155. So 155 is typically in the ballpark that most hydrocodes freeze out. So this is the temperature at which we convert the fluid into the particles. And since this thing, whatever it is largely in the blue region, we can say, well, actually, what was going on in the code was, under some sort of control. The right panel shows the inverse bulk Reynolds number, and because the bulk viscosity has a peak around the phase transition, we see that around this 200 MeV mark, that's actually where we put the peak in this simulation, you see some large inverse bulk Reynolds numbers. But once again, once you get up to this freeze-out hypersurface way up here, you're well into this dark blue region, and you're kind of happy, and you might be able to use linearized approximations for this F that's sitting here. So how well does this, the next question is, so where is, first let's look at here, but let me ask if there's any questions before I go to the next slide. Good. So can we understand what's going on here? This part, there's been a lot of work understanding why it's colored and not blue, and that has to do with just the rapid longitudinal expansion of the quark-gluon plasma itself as we create it, right? So what we do is we take two heavy ions, collide them at the speed of light, they pass through one another, and for a small amount of time before there's time for the transverse expansion to build up, the system looks like a one-dimensionally expanding universe. And what happens is if you were to measure the pressure along the beamline of direction, which I call the longitudinal pressure, over the pressure in the transverse direction, it wouldn't matter where you started here in the initial condition space. You would get drawn to a region that has a very large or small longitudinal to transverse pressure ratio. Now, as a function of time, transverse expansion kicks in, there's interactions between the particles, and they start to go back towards isotropy. But the fact that this is so small down here, that's why this is colored down here. So this is telling us that there's a large pressure anisotropy in the system. Now, despite this, again, because when we do it in practice, we run the code through there, and then we eventually reach this freeze-out hypersurface, and then we convert to particles. So how well does it work in practice? So this is just a typical hydro result. In this case, just for the identified particle spectra. So this is essentially the number of pions as a function of PT, number of kaons, number of protons plus antiprotons. And the curves that are going through here are a particular hydro implementation called anisotropic hydrodynamics. And what was done here is we fit just three numbers: the initial central temperature, the shear viscosity to entropy density ratio. In our case, this also fixes the bulk viscosity. So bulk is not a free parameter. And then we have to also specify the temperature at which we convert the fluid to particles. And then we tune that on essentially one on the most central class, and then we can make predictions for the other classes from the code after tuning three parameters. And as you can see, it works quite well as you go out in centrality until you start to get to these larger centrality classes, and you can see that there's some discrepancy. Now, these are interesting because these larger centrality classes are the ones that start to look like, say, a proton-lead collision, where the number of participants is on that same order. And we can see that at high momentum, something is going wrong in this freeze-out. And it's not just a hydro that gets this, it's every hydro. But at least for the central one, which is the kind of pretty pictures that I showed you, where it gets very dark blue at late times, we're kind of happy that things are going well. So let's look at another thing that's like these high impact parameter collisions, and that's an actual proton-lead collision at 2.76. And it's a similar space-time plot as the ones I've been showing you before, but it's done by the Frankfurt, Brazil, Finland mafia. And what they plot here is the Knudsen number. It's the driving force for the inverse Reynolds number. So but you can again, red is bad and blue is good. And the first thing you notice from this plot, from their PA simulation, is that there's no blue at all. It's all red. And even at very initial times, it's very red. That's because in this particular simulation, they incorporated the fact that the shear viscosity can depend on the temperature and is higher at high temperatures, then reaches a minimum, and then as you go back into the hadronic phase, starts increasing again. So you're unhappy at early times, you're unhappy at late times, and maybe there's some brief hope that you only have a 90% correction here or something, right, in between. And again, there's these freeze-out hypersurfaces shown, and if we look at the green, which is hovering somewhere around where people typically freeze out, you see that you're in a problematic region, and maybe you want to go beyond, linear order in your description of the distribution function, or do something even smarter, perhaps. Now, despite this, some people have just gone ahead and run their hydro codes and published papers that get presented in Quark Matter about it. That's fine. I'm okay with this strategy, but we always have to look under the hood. So this is a particular PA study by the, I guess I would call this the BNL crew and music and McGill guys. This is the average transverse momentum for different identified hadrons on the left as a function of the number of charged particles per unit rapidity. And on the right is showing V2 and V3 with different methods compared to experimental data. And now it's as a function of the number of offline tracks, which loosely correlates to the charge multiplicity. As we can see, as we get up in the ballpark, maybe above 50 or so, we might be touching all of the error bars, and it seems to be working. So this has led people to say, well, hydro is working at very low multiplicities. And it's great. Hydro is the winner, right? I'm a hydro fan myself, but when you look under the hood, which some referee forced them to do, so if you look in the paper, in the conclusions, there's a discussion of how large are the freeze-out corrections. And so they tried to quantify this. So if you look in low momentum, say pions, this V2, so that if you look on the freeze-out hypersurface for guys in this momentum range, you find that delta F is only bigger than F 10% of the time. So your hydro is breaking down only 10% of the time, or at least the freeze-out is breaking down. If you go up in momentum, what you find is this number increases 25, 45, until eventually at about 1.5, 50% of the cells on your hypersurface just had delta F greater than F. And it's worse than that because this is a measure of the magnitude. And if you plot the full distribution function now for the probability of delta F over F versus as a function of delta F, you see that there's some very large tails here, which are huge viscous corrections. But this part is particularly worrisome because the sum F plus delta F in this region is negative, which absolutely makes no sense, right? So you can't actually sample from a particle from a probability distribution function that's negative. In practice, people deal with this in different ways. Some people just cut out this region. Other people have some tricks to deal with this, to get rid of this and try to suppress these guys. Yes, go ahead.
That I understand, the blue curve is negative or what? Because these are logarithmic values.
Yeah, so anything over here below, so whenever the magnitude of delta F goes over F goes bigger than -1, that means F, the total F is negative over here. So these numbers are always positive, right? It's just that this region over here is the region. Now you could say it's, there's a low probability, but as you can see, as you increase the mass, it starts to flatten, when you increase the momentum. That's their stand-in for the momentum. They're increasing the transverse mass.
Mm-hmm.
So this is worrisome, right? And what we want to do, so one thing you might consider doing is just trying to add higher order terms. So go beyond this linear expansion in F and see if you can shrink this region somehow and improve the situation. The other thing you can do is to try to use kinetic theory itself, because again, what we're trying to do is convert this fluid to a particle. We can try to use the fluids into particles, yes. What we're trying to do is use kinetic theory information to inform how we do this. So what we want to do is run, in the end, a bunch of kinetic theory simulations in the far from equilibrium region, and then check at quote-unquote late times, what does the distribution function actually look like? In these simulations, we know that if we wait long enough, we will go to the hydro fixed point. But if we look at earlier times, the form of this correction might be dramatically different than the one we get from the linearized analysis. So that's the sort of practical goal. So the overarching theme is, can we improve hydrodynamics in far from equilibrium situations? And today I'll focus on freeze out itself. Other people, including myself, are also trying to improve hydrodynamics itself. So that's improving the equations of motion to make sure they work better in regions where the inverse Reynolds number is quite large. That's anisotropic hydrodynamics, essentially. And today I want to focus on this fundamental question: is there an attractor, which I'll define what attractor is, for the one particle distribution function if we just solve the QCD effective kinetic theory equations? And then, as I already alluded to previously, can we use information about that to improve our freeze-out description? Before I go to the meat of the talk, I want to pause and ask if there's any questions now in terms of motivation.
Mike,
yeah.
Sorry. Okay. What you show in the previous slide is only related to the corrections in the freeze-out surface. But actually, there is also the problem that at initial times and at times that people is running hydro, the Knudsen number makes no sense, yeah? So
at these early times, yes. But that large Knudsen number translates dynamically into a large inverse Reynolds number, which is what causes this breaking. Yeah.
Okay.
Yeah. So so essentially, the large inverse Reynolds number, again, going back here, tells us that pi is big, right? And whenever pi is big, that means that the linearized correction to delta F is also going to be big. So this region down here with the inverse Reynolds number, you probably have lots of stuff going negative, right? And that might happen here. You can see some regions where the one particle distribution function, even in heavy ions, is probably going negative out here when you do the freeze out here. But the bulk of the particles in a heavy ion collision don't come from here. They come from way up here, actually, right? So on this part of the hypersurface. So there's some error in lead, but it's an acceptable one. Yeah. When we go to this region, then you get worried. Yeah.
Okay.
Because now everything is red. And this is telling us that F will have large positivity violation everywhere, pretty much.
Okay.
So yeah, they're related. Does that answer your question?
Yeah.
Okay, good. I want to make sure. Any other questions? I don't want to get ahead of everyone's understanding. All right, good. So first, since I talked about the attractor, I have to introduce this concept, attractor, and what is it? So what I'm going to show you is some slides first in a simple kinetic theory model called relaxation time approximation first. The nice thing about this simple kinetic theory model is that for Bjorken expanding matter, it turns out you can solve this thing exactly by iteratively solving an integral equation. So these plots that I'm showing you are actually exact solutions to this problem. So it's always good to start with an exact solution. So in this case, with this exact solution, I can start the system with different levels of pressure anisotropy, and for a given assumed value of E/S, I can plot this PL over PT as a function of time. And the first thing that we see is that all solutions rapidly become momentum space anisotropic. Again, that's this early time expansion. And then they only slowly, as a power law in this Bjorken case, approach isotropy from above. If we do the same thing, but with a larger E/S, we see that, qualitatively it looks the same. All solutions become highly momentum anisotropic and slowly relax back towards equilibrium. And note that this is essentially the timescale for the end of a lead-lead collision, roughly speaking. We can combine these two plots onto one, and you can see some sort of semi-universal features arising from this, that all the ones with 8/S group into one set, and all the ones with 8/S is one group into another. But something even better happens if I rescale this time axis in this case by dividing time by what's called the local relaxation time. So in the relaxation time approximation, that relaxation time is just given by 5 eta bar, where this is eta/S, divided by t. So this is just a constant in these simulations. What's important is that we just take tau times the local effective temperature, and this turns out to be the inverse Knudsen number itself. So early times over here is large Knudsen number, and over here is small Knudsen number. Yeah. Okay. So with this rescaling of the time variable, we can now plot both results for eta/S is 1 and eta/S is 2 on the same plot. And what we can see is they're sort of starting to tell us that there's some universal curve that extends from very small bar omega in this case up to the time. They've all collapsed at this late time, that's for sure. That's different than what we saw before over here, right? So there's something non-trivial going on here. Physics-wise, what's important here is that this is representing the loss of the initial condition of the information, at least some part of it. And by some time here, all solutions have now collapsed down to this universal thing we call the attractor. Numerically, what you can do is just start varying eta/S around and start collecting a whole families of curves, and also vary the starting time, and you'll eventually be able to construct this curve, which I've indicated on the next slide is this black line. It's called the attractor. In RTA, it's unambiguous to extract this line. In some theories, there's some ambiguities and people argue over them. In this one, it's crystal clear. And now I showed just the different initial conditions as the dotted line. Again, this is the exact solution to the problem. And as we can see, they all collapse to this attractor. And in this particular case, we see that it collapses to an attractor at a time before we start being described by first-order viscous hydro, which is this Navier-Stokes solution. I can improve this a little bit by doing second-order viscous hydro and then get this curve to come a little bit further along the black curve, and then it will go away from it. But what is suggestive here is that there might be an early time attractor that continues beyond where hydro works all the way to time is equal to 0. And if we know information about this attractor, we might be able to then fix delta F. That's the basic idea. Now, as I emphasized, if we go to very late times on this, we're into this sort of first order hydro regions. This is the quote unquote universal region. It doesn't matter what microscopic model you use here, as long as it's interacting and you've tuned the shear viscosity to match between model A, model B, model C. You'll always get this result out here. This is hydro. At early times, this part over here completely depends on the microscopic model. And so, but it seems in most, not all, let's see, all kinetic theory models at least, there seems to be some universal, some curve that emerges in each of those sets. It's not universal, but they're qualitatively similar, and they exist. Now, we also wonder about this time, right? Because this is the time scale over which all of this action is happening in a PA collision. So they freeze out roughly after about 4 Fermi over C. So what we want to do is try to construct some effective kinetic theory, either straight kinetic theory or kinetic theory improved hydro that can better describe this region and maybe push back even further. Good. And but before that, we have to ask, in each model, I just showed you RTA, does a unique early time attractor even exist, right? So this is a sort of mathematical question. And some people have now been looking at a variety of different models. This is some plots from a paper from Kirkala, Vandershee, and Wiedemann and Wu. It came out last year. They're showing a similar quantity here, which is the longitudinal pressure over the energy density in all three panels. The left panel is Israel-Stewart hydrodynamics. The middle panel is this exact solution to the RTA. And the right panel is using some ADS-CFT numerical simulation done by Vilke Vandershee. And what they wanted to show in this sequence of plots is that you can construct this attractor by varying not just the initial, the eta over s, you can also vary the initial time. So in each of these curves, what they did was keep eta over s fixed and just vary the initial time. And as you can see, as we go to earlier and earlier times, we collapse to this attractor. And as we move forward in time, we see that all curves are sort of, and this is a way that we can now trace out this attractor curve again. The other surprising thing from a plot like this is a log scale on the horizontal axis, is that in this model and in this model, what we see is that the time for the approach to the attractor, which is this short time scale here for the black curve, gets smaller and smaller as tau naught is decreased. So these solutions that started very early, they converge to the attractor very early. So this is our basic criteria for the existence of what's called an early time or a pullback attractor. Now in Israel-Stewart, we notice that this ratio PL over the energy density actually went negative right around here. That's telling us again that pi became too big, and tells us something about the breakdown of this particular hydrodynamic model, because the underlying physics that was being modeled here was actually this RTA. They just did the Israel-Stewart version of RTA. It should agree with this curve, and it doesn't, right? So you can see that there's some region at early times that the hydra breaks down. Now, before I get to the third panel, which I'll come to in a second, I want to bring you down to the next panel in the lower left. So this was RTA. My student Dekriat and I were also able to do the attractor extraction in a different kinetic theory. This is scalar, either including the quantum Bose enhancement or Fermi suppression effects, or the classical just with Boltzmann statistics. And in that case, we were able to demonstrate that you could extract these early time attractors for non-trivial kinetic theories. Again, there's some quantitative difference between these attractors, but qualitatively they all look the same. All the plots, if I didn't tell you what was what, they would look like this. Yeah. Now, there's this one. Let's go to this one next. So here, what they've done is shown dashed lines and solid lines, and the dashed lines are one particular kind of ADS initial condition for the functions as a function of the bulk variable, and the solid is a different choice. And what they found was that with these two different choices, although there was a kind of pullback attractor that seemed to exist for each, they weren't unique. And that if I chose this guy, this particular set of initial conditions, it looks dramatically different than this one. Now, the difference physically here, as my understanding, is that this set of initial conditions has a large amount of two-body correlations in it. And so then the question becomes whether that amount of two-body correlations is in fact physical. Is that degree of two-body correlation really in the initial gluonic wave functions that are generated from CGC? If not, I don't know if this is really a kind of physical initial condition that we can really talk about. It may be some kind of artificial result by taking two large two-body correlations. I don't know. In kinetic theory, there are no two-body correlations by assumption, because you are dealing with the one-particle correlation function. So this distinction is not even a question that we can ask in the kinetic theory. The question I want to focus in the kinetic theory is can we extend this now from RTA, as we did with scalar, to QCD? But before I do that, I want to focus a little bit more on RTA itself. Now, the other thing, as I alluded to, that you can do with these attractors is that if you know the exact solution and then you can come up with a hydro approximation, you can test hydro approximation against the exact solution. So this is such a plot. I'm sorry, but the variable is different. It's related to PL over PT. It's essentially PL over PT upside down. It's a choice that was made by some Polish guys, and I just stuck with their notation. The exact solution in RTA is this orange dotted curve here. And then there are various hydro approximations. First order viscous hydro, this Israel Stewart that I just showed you. Then if you do what's called DNMR, which is the complete second order version, Mueller-Israel Stewart's missing some terms, you get closer to the exact solution. If you go to third order, you get, I don't have it on this plot, you get closer to the even closer. And if you do this thing called ahydro, you're sitting on the exact solution. In this case, ahydro works the best because it actually resums an infinite number of terms in the inverse Reynolds number. Nowhere in the ahydro derivation was the inverse Reynolds number actually assumed to be small. So that's the reason that it actually works the best. So once we've determined these attractors, in this case, in the RTA one, we can test different hydro approximations. But when I saw this a few years ago, I started asking the question, well, if this attractor stuff exists for the thermodynamic variables, like the pressure ratios and stuff, does it exist for other variables in the system? So as we've seen, there seems to be an attractor for T mu nu, right? And T mu nu describes only 14, T mu nu, the energy momentum tensor plus the number density and the diffusion current, they only describe 14 degrees of freedom. In kinetic theory, at least if we have on-shell particles, then we have an on-shell one-particle distribution function that's a continuous function that has, in principle, an infinite number of degrees of freedom. In kinetic theory, how we cook those infinite number of degrees of freedom in F down to some finite number of degrees of freedom is doing this procedure of taking moments of the Boltzmann equation. So this is the second moment of the Boltzmann equation, and it will give you the energy momentum tensor, where dp is the invariant phase space integral. So the natural follow-up question for me was, what if I start throwing more powers of p in here? Do I see attractors in higher rank tensors, which involve higher powers of p, in particular ones that are sensitive to higher momentum parts of f here? And if there's an attractor for the moments that describe the higher momentum parts of f, we can use that to try to fix what's going on wrong in the high momentum freeze-out. So in what I'm going to show you today, I'm going to focus on yet a simple system. It's undergoing Bjorken expansion. It's conformal. It's transversely homogeneous. If it's conformal, you can always reduce this set of general moments down to a set of this type that have index n and m, where n is the power of the energy, essentially, and m is the power of the longitudinal momentum squared. There could be ones with the transverse momentum here, but you can use the conformality to always express those in terms of this set of moments. So this represents a complete set of moments that I can now decompose F into. They're not orthogonal or anything fancy, but they're complete. Now, some of these are ones that we know from the literature. For example, if I look at M20, that's just E squared integrated over dP. That's nothing but the T00, otherwise known as the energy density. And if we do M01, that's just the longitudinal pressure in the local reference frame. The other ones don't really have, some of them do, only one other has a hydrodynamic interpretation. I'll show it on some slides. The rest of them don't have a hydrodynamic interpretation because they don't map to conserved quantities. So this is what an attractor plot now looks like in terms of these moment variables. And I've added a bar here. So what I did was I took the moment from the simulation of the one particle distribution function as a function of this time variable. And then I rescaled it by its equilibrium value at that time using the energy density that the simulation gave me. In this case, the exact solution to the RTA. As we can see, this approach is 1 as we go forward in time. This is the equilibration of the longitudinal pressure, the isotropization of the system. And as we saw before, if we vary around the initial condition, they collapse to this black line that's hiding underneath. But now I can not only do this for m for this particular ratio, I can do it for a bunch of them. And I'm only showing you some of the zoo of things I collected in this paper. So there are some that are familiar. So this one, M, this is related to the in-medium screening mass. This is the number density divided by the equilibrium value. This is the energy density divided by the equilibrium value. It's 1 as it has to be if your simulation conserves energy. So this is just a check. This was that one that we've seen before. And then as we move down and to the right, these are moments that are sensitive to more and more high momentum parts of the distribution function. As before, we've rescaled the horizontal axis by plotting it as tau over tau r. And what you see is that all of these moments collapse. And they all collapse on approximately the same time scale. If you are careful and go and zoom and measure, you'll find actually that the higher moments in RTA actually collapse faster. And when I got this out, what it told me, well, I kind of knew it before I got this out, was that there's not only an attractor for the moments of the distribution. If they all collapse, there must be an attractor for the entire distribution function. So I wrote, you can either extract it from those moments, or you can just write a code to extract the full attractor for the one particle distribution function. The top panel is showing this. This is now as a function of transverse momentum here, longitudinal momentum divided by the instantaneous temperature T. And we see two pieces. One is this very narrow peak here. This is this highly anisotropic squeezed piece, which comes from particles that, the population of particles that never had any interactions whatsoever. So this is the kind of free streaming part. And this part is the equilibrating part. And as we move to the right, we can see that this is becoming more equilibrium-like, but it's not in perfect equilibrium. The left shows a generic solution, which is not an attractor solution. This, I just started with some momentum anisotropy, some spheroidal deformation. And as we evolve it forward in time, we notice that this thing starts to look like this more and more as a function of time. So either way you want to look at it, from these nice contour plots or the collapse of all of these moments, in RTA at least, there's an attractor for the entire distribution function. And if we know information about this attractor, then we can try to improve freeze-up, to repeat my main point. Now, the other thing I said is once we know these attractors, we can also test different hydro theories. So here's a panel of hydro tests. This was the one that we were looking at so far. There's a black curve, which is the RTA attractor. There's a green dashed, which is the first order hydro. DNMR is the blue dashed curve, and then A hydro is the red dashed curve. So as we saw for this moment, A hydro sort of hits it bang on, and the different normal linearized hydro streams break down at early times. And as we move down into the right, we notice that these guys break down earlier and earlier. That's to be expected because the high momentum part of the thing is not described well in this case. A hydro also breaks, as you can see in the high momentum moments. It also doesn't do as well. It doesn't describe the exact solution as well as the low moment moments. But it's better than the other guys. Yeah, so we can have some practical conclusions from these guys. So now to come to the punchline. Does a similar thing exist in QCD? So to answer this question, what we did was reach out to Alexei Kirkala because he had written a nice paper with Yan Shu in 2015, and then there were some follow-up papers after this with many co-authors, in which what they did was write a code to solve what's called the Amy effective kinetic theory. So Amy is Arnold Moriafi. They derived this effective kinetic theory to describe the high temperature part of the quark-gluon plasma evolution. You can reduce it down to a Boltzmann equation with an effective 2-to-2 collision kernel, a splitting, which takes into account LPM suppression and also detailed balance. And this code has been tested at least earlier in reproducing all of the hydrodynamic moments, and it works well. So what we did in practice was reach out to Alexei and Jan, get their code, and then added just the measurement of these moments, and then had to use very large grids because some of these moments are sensitive to rather fine details of what's going on in the distribution function. So this was the old plots, same thing, M01 bar here, M01 bar here. This is now the QCD result. And again, for your eye, I put the first order gradient expansion, and we can see that on this rescaled time axis at around 1, it starts working, but we can see there's some curve that extends back further in time. Now, there's two sets of black curves. One is starting with just a spheroidally deformed thermal distribution, which I call RS, Ramachka-Strickland form. And the other one is an overoccupied CGC initial condition with all the parameters fixed to some calculation done in Jovoskyla or by Jovoskyla people. And you notice that at early times, there's some difference between these two types of initial conditions, but then again, by about roughly 0.3 on this dimensionless scale, they collapse down. And so this is now evidence, not full evidence, for the existence of this attractor in QCD. So before showing you the next slides, because there's a dimensionless time variable, I think it's important that we all get our bearings now for the plots. So what are these times in practice? So if you assume that you're modeling a lead-lead collision at 5.02 TeV, you can make a map from this scaled time. You just need to know essentially what's the initial temperature, and then you can make a map from here to here. So for this for LHC type collisions, 0.2 on this scale is roughly 0.3 Fermi over C. 0.5 on this scale, which if I can count it, 2, 3, 4, 5, that's here, that's 1 Fermi over C. And then 1 that's sitting here, that's 2 Fermi over C. Now, by the time we get out to 5, 1, 2, 3, 2, 3, 4,
Mike, are you back?